Welcome, health data detectives, to a crucial investigation in our machine learning series. I'm excited to be here with you. And today we're diving into a classification task using an interpretable model from the Interpret library. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we explore a dataset about diabetes risk. Let's start by setting up our environment and gathering our tools to begin this health-focused journey. I begin by installing the Interpret library in Colab with pip3 install interpret. This library is our key to explainable AI, helping us understand our model's decisions with clarity. Next, I import the essentials. NumPy for numerical operations, pandas for data manipulation, Seaborn for potential visualizations, and requests and string.io to load our dataset from an online source. From sklearn, I bring in train test split to split our data and accuracy score and classification report to evaluate our model's performance. From interpret, I import explainable boosting classifier from the Glassbox module, our star model for today, along with the show function to display explanations. I set up inline visualizations with set visualize provider and inline provider, ensuring our plots rendered directly in Colab. With our toolkit ready, let's load the data. I load the Pima Indians diabetes dataset from an online source, a URL hosted on GitHub. I use request to fetch the data and pd_read_csv with string.io to parse it into a data frame, assigning column names, pregnancies, glucose, blood_pressure, skin_thickness, insulin, BMI, diabetes_pedigree, age, and outcome. I print data.head to take a look. The first row shows pregnancies 6, glucose 148, blood_pressure 72, skin_thickness 35, insulin 0, BMI 33.6, diabetes_pedigree 0.627, age 50, outcome 1, indicating diabetes. The next row has pregnancies 1, glucose 85, BMI 26.6, outcome 0, no diabetes. This dataset, collected from the Pima Indian population in Arizona, contains 768 records of women aged 21 and older, with features like number of pregnancies, glucose levels, and BMI, and a binary target, outcome, where 1 means diabetes, 0 means no diabetes. About 35% of the samples are positive, making it a slightly imbalanced but rich dataset for studying diabetes risk. Let's prepare it for modeling. I separate the features and target. X is all columns except outcome, including pregnancies, glucose, blood_pressure, skin_thickness, insulin, BMI, diabetes_pedigree, and age. These health metrics will help us predict diabetes. Y is the outcome column, our binary target. I split the data using train test split, allocating 20% for testing and 80% for training, with random state 42. This gives us 614 training samples and 154 test samples, with roughly 99 non-diabetes and 55 diabetes cases in the test set, based on the dataset's 65-35 split. The data is already numeric and clean, no missing values to handle, as the dataset uses 0 for missing measurements like insulin, which we'll treat as valid for now. We're ready to train our model. I initialize the Explainable Boosting Classifier, or EBC, from Interpret's Glassbox module. EBC is part of the Explainable Boosting Machine, EBM, framework, which combines boosting, iteratively improving weak learners, with interpretability. Unlike traditional boosting models like XGBoost, EBM uses generalized additive models plus interactions, GMs, fitting simple functions for each feature and their interactions, making it highly transparent. EBC is tailored for classification, predicting binary outcomes like diabetes while offering clear explanations for each prediction. I call fit on xtrain and ytrain to train the model, letting it learn how features like glucose and BMI predict diabetes. Once trained, I make predictions on xtest with predict, storing them in ypred, and evaluate with accuracy and classification report. The accuracy is 0.7403 to 74.03% correct predictions. The classification report shows, for class 0, no diabetes, precision 0.80, Recall 0.80, F1, score 0.80, support 99 for Class 1 diabetes. Precision 0.64, recall 0.64, F1, score 0.64, support 55. Macro average F1 score is 0.72, weighted average 0.74, decent performance. But the lower scores for Class 1 reflect the challenge of detecting diabetes due to imbalance. Next, I explore the local explanation for the first test sample to understand the model's prediction. I call EBR score classifier.explain local on x test slice 0 to 1 and y test slice 0 to 1. Extract the explanation data with local explanation.data 0 and print the details. Predicted 1, diabetes. True value 0, no diabetes, a misclassification. Feature contributions show age at 0.994. The strongest positive push toward diabetes, likely because the patient's age is high. BMI at 0.320 and insulin at 0.316 also push toward diabetes, indicating higher risk. Glucose at minus 0.833 pulls strongly against diabetes, perhaps a lower glucose level. Blood underscore pressure at minus 0.086 and glucose and skin underscore thickness at minus 0.066 also reduce the score. Positive interactions like blood underscore pressure and BMI at 0.277 and insulin and age at 0.265 boost the diabetes prediction. On screen, you're seeing the local explanation plot, a bar chart for this prediction. The age bar stretches far right in orange at 0.994, driving the diabetes prediction. BMI and insulin, also in orange, add 0.320 and 0.316. Glucose, in blue, juts left at minus 0.833, countering the prediction. Smaller bars like blood underscore pressure and BMI in orange at 0.277 show interactions, with the final prediction of 1 marked at the top, a clear view of why the model chose diabetes, despite the true label being 0. I move to the global explanation to understand the model's overall behavior. I call EBR classifier.explain global, extract the global feature importance data with global explanation.data, and print the values. Glucose leads at 0.651, the most influential feature. BMI follows at 0.493, age at 0.416, and diabetes underscore pedigree at 0.277. Insulin is 0.178, while blood underscore pressure and skin underscore thickness are lower at 0.060 and 0.074. Interactions like glucose and skin underscore thickness at 0.291 and blood underscore pressure and BMI 0.186 also matter. I display the plot with show, and on screen, you're seeing a feature importance graph. The glucose bar towers at 0.651 in blue, stretching far right. Glucose levels are critical for diabetes prediction. BMI at 0.493, also in blue, is a strong second, followed by age at 0.416 and diabetes underscore pedigree at 0.277. Smaller bars like insulin at 0.178 and blood underscore pressure at 0.060 show their lesser roles. Interaction bars like glucose and skin underscore thickness at 0.291 highlight how feature pairs refine predictions. This plot confirms glucose, BMI, and age as the primary drivers of diabetes risk across the dataset. Let's reflect on these outputs. They're a health report for our model. The head showed a 50-year-old woman with 6 pregnancies, glucose 148, BMI 33.6, outcome 1, diabetes, while the next had glucose 85, BMI 26.6, outcome 0, no diabetes. Accuracy of 0.7403 means 74.03% correct predictions, 114 out of 154 test samples. The classification report details. Class 0, no diabetes, has precision, recall, and F1 score of 0.80 for 99 samples, strong performance. Class 1, diabetes, has 0.64 across all metrics for 55 samples, harder to predict due to fewer cases. The local explanation predicted 1 for a true 0, with age 0.994 and BMI 0.320, pushing toward diabetes, but glucose minus 0.833, pulling against, a misstep possibly due to an unusual glucose value. Globally, glucose's importance of 0.651 aligns with medical knowledge. High glucose is a diabetes hallmark. BMI at 0.493 and age at 0.416 reflect their roles in risk, while interactions like glucose and Skinner score thickness at 0.291 show how feature pairs matter. EBC's transparency lets us see exactly how these health metrics shape diabetes predictions. To wrap up this health investigation, we've analyzed the Pima Indians Diabetes Dataset, a 768-record study of diabetes risk, and trained an explainable boosting classifier, achieving an accuracy of 0.7403 and a macro F1 score of 0.72. The local explanation revealed age and BMI driving a diabetes prediction, tempered by glucose, while the global view confirmed glucose, BMI, and age as key risk factors. EBM's interpretable approach, breaking predictions into additive contributions, makes EBC a powerful tool for classification, balancing accuracy and transparency. Grab this code, experiment with feature engineering, and dive deeper into diabetes prediction. I'm inspired by this health-focused analysis. Hope it's got you thinking about data's role in well-being. See you next time for another life-saving data dive.